all, welcome to Chapter 2, Section 1 for Newton's first and second laws. All right, today we're going to talk about what makes an object's motion change, what is inertia, and what affects how much an object speeds up or slows down. So what are Newton's laws of motion? Imagine rolling a basketball across a smooth wooden floor. How far will the ball roll before it stops? Now imagine rolling the ball across a floor covered with carpet. The ball will not roll as far as the carpet as it did on the smooth floor. What causes this? Hundreds of years ago, an English scientist named Sir Isaac Newton noticed similar effects. He also wondered what caused them. He discovered the relationship between motion and forces. He described the relationship in three ways. Today we call these laws Newton's laws of motion. Okay, what is Newton's first law of motion? A ball that stops after rolling along the floor is an example of Newton's first law of motion. This law states that an object's motion will change until an unbalanced force acts on the object. The law also states that an object will not start to move until an unbalanced force acts on it. A rolling ball stops moving because the force of friction acts on it and slows it down. If there were no friction, the ball would keep rolling. So here in this example, the bowling ball slows down as it rolls because the force of friction. If no forces act on the ball, it would not stop rolling. Okay, so let's look at our reading check. State Newton's first law in your own words. Okay, so you can write this down if you want. Or you can stop here, write down what you want, and then check it with me later. The motion of an object will not change unless an unbalanced force acts on it. Okay, so a ball in motion stays in motion. A ball at rest will not move until something acts upon it. Okay, so what is inertia? Another way of stating Newton's first law is that matter resists any change in motion. All objects resist changes in motion. However, not all objects resist changes in motion by the same amount. For example, it does not take very much force to change the motion of a baseball. It takes much more force to change the motion of a bowling ball. The bowling ball resists changes in motion more than the baseball does. The tendency of an object to resist change in motion is called inertia. All objects have inertia. The amount of inertia an object has depends on the object's mass. The greater the mass of an object, the greater its inertia. Okay, so here's reading check number 2. How was mass related to inertia? So you can pause here, write it down, and then check your answer with mine. Okay, pause. All right, welcome back. As mass increases, inertia also increases. Well, that didn't help much now, did it? Increases. Okay, so as the size or the weight or the mass of something increases, inertia also increases. So it takes more force to make it move. Okay. Seat belts and car seats. Think about the last time you rode in a car. What happened when the car stopped suddenly? You probably felt like you were being pushed toward the front of the car. Objects in the seats near you may have fallen over. Newton's first law of motion explains why this happens. When a car stops, the inertia of the object inside the car prevents them from stopping right away. Therefore, they may slide or fall over as the car suddenly stops. Seatbelts help to protect people inside a car from being hurt. when the car stops. When the car stops, you start to slide toward the front of the car. The seatbelt catches you and stops you from sliding. Car seats help keep babies from being hurt when a car stops. These seats face toward the back of the car, so as you can see in the figure below, this kind of car seat keeps the baby from sliding forward. Car seats like this one help prevent babies from being hurt when a car stops. Okay, so look closer. How does the car seat protect the baby? Take a minute to write down your answer. So pause the screen and then come back when you're ready and we'll talk about the answer. All right, pause. Okay. The car seat keeps the baby from sliding forward when the car stops. Okay? All right. So let's talk about what is Newton's second law of motion? Newton's first law describes what happens when no unbalanced force acts on an object. The object's motion does not change. What happens when an unbalanced force does act on an object? Newton's second law states that the larger the unbalanced force of an object, the more the object's motion will change. It also states that the larger the object's mass, the smaller its acceleration will be. Acceleration is this change in motion of an object. Think about a baseball. If you throw the baseball gently, it will not move very fast. If you throw it with more force, it will move much more quickly. Now imagine using the same force to throw a bowling ball. What will happen? The bowling ball will move much more slowly than the baseball. We write Newton's second law of motion as a mathematical equation. So net force equals mass times acceleration, or F equals ma. You can use this equation to calculate how much force is needed to make an object accelerate. You can also use it to calculate how much an object will accelerate when a force acts on it. Before you can use the equation, though, you need to know how scientists measure force. Okay? So, in many cases, large trucks move more slowly up hills than small cars. Why do you think the reason is? So go ahead, jot down your reason, and we'll be back to talk about it. So go ahead and push pause. All right, welcome back. Trucks have more mass. Okay, so they need more force than a small car does to move. Oops, let's put it on here. To move up a hill. Okay, so we know that the larger it is, the more force it takes. So the truck is larger, so it takes more force to go up the hill. Okay. What are units of force? The SI units scientists use to measure force is the Newton. 1 Newton is the amount of force needed to make 1 kilogram mass accelerate at 1 meter per second squared. So look at this. Newton equals kilogram times meter per second squared. So if you see this kilogram times meter per second squared, you know that it's the same thing as a Newton. Okay, although scientists use newtons to measure force, sometimes people use pounds instead. 1 pound is equal to 4.45 newtons. 1 newton is equal to 0.225 pounds, okay? Let's answer this up here. How many newtons are equal to 10 pounds? Go ahead and push pause and answer this, and we'll be right back. Okay, so I'll come back. So we know that 1 pound equals 4.45 newtons, and we want to know how much it equals for 10 pounds. So we multiply it by 10, and we get 44.5 newtons. All right. Okay, how does mass affect acceleration? Look at the two objects below. below. The football players are pushing with the same force in both pitchers. However, the mass on the sled is smaller in the pitcher on the left than the one in the pitcher on the right. Therefore, the sled on the left accelerates more than the one on the right. Okay, so you can see this one, they don't have people standing on it, and on the one on the right, they have people standing on it. Okay, so the force is the same, and it's still going to accelerate, but the left is going to accelerate much faster. Okay. 6. What could the football players pushing the sled do to make it move more quickly? All right, take a minute to think about that, and we're going to answer that. So go ahead and push pause. Okay, they could push with a greater force. So if you increase the force, you would increase the acceleration as well. Okay. So how does force affect acceleration? Okay. Look at the other two pictures below. In the picture on the left, one person is pushing the car. The car has a large mass and it does not accelerate very much. In the picture on the right, several people are pushing the same car. The mass of the car is the same as the left-hand picture. However, the force is greater. Therefore, the car on the right accelerates more. Okay? So, what would happen if the mass of the car on the right was greater? Take a minute to think about it and write down your answer, and then come back and we are going to check it. Okay, so it would accelerate less. We know that as the mass increases, it's going to take more force, and then that would make the acceleration less as well. Okay? All right, so calculating acceleration, calculating force from acceleration. Zookeepers lift a lion on a stretcher. The total mass of the lion and the stretcher is 175 kilograms. The acceleration of the lion and the stretcher is 0.657 meters per second squared upward. What force do the zookeepers use to produce this acceleration? So what do we know? So let's look at what we know. We know what the mass is, and we know what acceleration is, but we don't know force. We know the equation. Force equals mass times acceleration. So they did 175 kilograms, which is the mass, times acceleration at 0.657 meters per second squared. And we end up, when we multiply them, with 115 kilograms times meters per second squared. But remember, kilograms times meters per second squared is the same as newtons, so they can write it as 115 newtons. Okay, let's look at our math skills here. An object with a mass of 10 kilograms accelerates upward at 5 meters per second. What force acts on the objects? Okay, so let's write down what do we know. Okay, okay. We know that mass is 10 kilograms. We also know that our acceleration is 5 meters per second squared. Okay, and we know F equals ma, so we know force equals 10 kilograms times 5 meters per second squared. Okay, so we know that force equals 50 kilograms times meter per second squared, or we could write it as 50 newtons. Okay, all right, let's look at our next example here. Calculating acceleration from force. A sailboat has a mass of 655 kilograms. A force of 895 newtons pushes the sailboat forward. What is the sailboat's acceleration? So what is it that we know? We know that we have 655 kilograms. We also know that our force is 895 newtons. What we want to find out is acceleration. So our formula is force equals mass times acceleration. we now need to solve for A. So you can see that they divided by m on both sides, and we get A equals, or acceleration equals force divided by mass. So our mass, or our force, is 895 newtons divided by 655 kilograms. So we're going to change newtons back into the kilograms times meters per second squared. The reason we do that is so that we can cancel out the kilograms, and when we divide, we end with 1.37 meters per second squared. Okay? Show how to rearrange the equation of Newton's second law of motion in order to solve for mass. So we know that force equals mass. Force equals mass times acceleration. Okay. So what we're first going to do is we're going to say force equals mass times acceleration. So what I want to do is I want to divide this side for acceleration. Okay. I'm also going to then take this side and take A divided by force. When I cancel this out, what I'm going to be left is mass equals force divided by acceleration. All right, this is the end of section 1. Homework for tonight is actually section 1 review and the concept review. What I want you to do also is to get started on this problem set, because this problem set, the math skills, and all these problems we're going to work on them tomorrow. So please see if you can solve these before we get to it tomorrow. Okay, I'll see you later. Bye.